Okay, now I've got the system in an equilibrium position here. I'm going to take this mass off of the hanger, and then I'm going to hold the mass here and drop it. And you see what happens. Now this is of course a damped oscillation, and we're not dealing with damping very much. And I know how disappointing that is to some of you. We'll try to throw an extra credit problem onto the final to see if you can handle that. Okay. The system is at this position. And of course, its system's going to change when we drop this weight on. And its equilibrium position is going to go from here down to here. Now, when I drop the weight on here, what happens? Oh, weight slides off. Okay, let's pause a second. Well, actually, I've got another weight here. I don't have to pause. Okay, let's see if I can get it to hang on there. This is a little bit tricky. I dropped it from a pretty good height. Let's see if we can. Okay, good. Now, what happened was the oscillation extended down here further than this distance. Okay, so what we're doing is we're essentially beginning the oscillation of the system at this point with some non-zero initial velocity. Now let's just see if we can mark how far the system goes down. Okay, we went down to about here before everything went to heck. So I'm going to say that in the case of this system, we achieve this amplitude. That's our amplitude A. Here's our equilibrium. I'll label that Y sub EQ. And here is our Y naught. Now, the mass of the system is 0.1 kilogram, and the force constant is 4 newtons per meter. What I want to know is if Y equals Y naught, T equals 0, what is the equation of motion in terms of the amplitude and the other quantities that make up the equation of motion? Well, the equation of motion is Y equals A cosine of omega t plus theta naught. Omega is the square root of k over m. We know what k is. We know what the mass is. If we divide k by m, we get 40, and it's going to be 40 meters squared. I'm sorry, 40 seconds squared, 40 reciprocal seconds squared. The square root of that is very close to 2 pi. So from this we can calculate omega. The only thing, and we can measure A, so the only thing we have to determine is theta naught. Okay? So omega is the square root of k over m, and again we can calculate that. That's going to be a known quantity. A is known. We need to find theta naught in order to arrive at our equation of motion. So you should, excuse me, pause for a second and see if you can do that. I'll resume here in just a minute. Okay, it's not particularly difficult to find this. Y of t equals y naught when t equals 0, so we have y naught equals a times the cosine of omega t, but since t equals 0, omega t is 0. That's just theta naught. So we have cosine of theta naught equals y naught over a, so that theta naught equals the inverse cosine of y naught over a, or the inverse cosine of y naught over a plus 180 degrees. Okay, well, now let's go ahead and do some measurements and see what y naught is, see what a is, and see what theta naught would be. Let me comment that theta naught is the inverse cosine of y naught over a, so our reference circle model has y naught here, a being the radius of the circle, so that theta naught is either this angle or this angle. So theta naught could be this, or it could be this. If motion is in the counterclockwise direction, then if theta naught is this, then y naught would be decreasing at the initial instant, because we'd be here on the reference circle. Our motion vector in the reference circle would be in this direction, and y naught would be decreasing, whereas if it's here and we're moving in the counterclockwise direction, the horizontal component of this velocity vector would be positive, so y naught would be positive at the initial instant, not y naught, but v naught. Y naught would be increasing at the initial instant. Okay. Well, how do we put that together, and how do we put that together with our measurements? We'll do that in another clip, but you should think through these questions and think through how we're going to come up with a solution once we've measured these two distances.